Section 1.9 is patterns, equations, and graphs. I can use tables, equations, and graphs to describe relationships. Big ideas here. Sometimes the value of one quantity can be found if the value of another is known. The relationship between the quantities can be represented in different ways, including tables, equations, and graphs. We can use an equation with two variables to represent the relationship between two varying quantities. A solution of an equation with two variables x and y is any ordered pair x and y that makes the equation true. Remember, with ordered pairs, they're alphabetical, so x comes before y, always. So here we want to know, is 310 a solution of the equation y equals 4x? And we're going to do these similarly to how we did them before when we had like x equals 3 that we substituted in, except here we're going to substitute in both values. So remember, ordered pairs are x and then y. And once we substitute these in, we're going to check, is it a solution? Does it make a true statement? If it does, it's a solution. If it doesn't, it's not. So here, our ordered pair is x and then y. So what it tells me is x equals 3 and y equals 10. So I'm going to go over to my equation, and instead of putting a y, I'm going to put a 10, because we know that those mean the same thing here. And instead of putting an x, I'm going to put a 3. And now we're going to simplify this and see if it gives us a true statement. If it does, it's a solution. If it doesn't, it's not. So 10 equals, on my right side, I can simplify that expression to be 12. And we check, does 10 equal 12? Nope, they're not equal. So is this a solution? No. Now, is the ordered pair a solution of the equation y equals 4x? We're going to check here. Remember, ordered pairs are x and then y. So I have x equals 5 and y equals 20. And I'm going to plug those into my equation. So instead of y equals 4x, I'm going to replace my y with what y equals, 20. And instead of 4x, I'm going to replace my x with what x equals, 5. And since 4x means multiplication, we're going to multiply our 4 and our 5. And I'm going to get 20 equals 20. We check, that is true, which means, is this a solution? Yes. Same idea here on B. We keep our same equation. Remember, ordered pairs are x and then y. So x is going to be negative 5 and then y is going to be negative 20. Now, everywhere that I see a y, I'm going to plug in a negative 20. Everywhere I see an x, I'm going to plug in a negative 5. Now we simplify both expressions. Our left is already simplified. On the right, we can multiply. When we multiply a positive and a negative, we get a negative answer. And negative 20 does equal negative 20. So since this is a true statement, it means that yes, the point negative 5, negative 20 is a solution. In C and D here, again, we're using the same equation. Ordered pairs are x and then y. So here I have x equals negative 20 and y equals negative 5. So I'm going to plug my negative 20 in for my x. And I'm going to plug my negative 5 in for my y. We're going to simplify both sides of our equation, both expressions. My left expression is just negative 5. On the right, again, when we multiply a positive and a negative, our answer is negative, so negative 80. And if we look here, negative 5 does not equal negative 80. So since this makes a false statement, it is not a solution. And in D, same equation. Ordered pairs x, y. X is 1.5. Y is 6. Simplify our expressions, I get 6 equals 6, which is true, which means yes, this is a solution. We can represent the same relationship between two variables in several different ways. So in example 2, we're going to use a table, an equation, and a graph. Both Carrie and her sister Kim were born on October 25th, but Kim was born 2 years before Carrie. how can we represent the relationship between Carrie's age and Kim's age in different ways? If we look here, Kim was born 2 years before, which means Kim is older and Carrie is younger. So when Carrie was born and was 0, Kim was 2. When Carrie was 1, Kim was 2 years more than that, or 3. When Carrie was 5, Kim was 2 years more, 7. When Kim was 10, Carrie was 2 years younger and was 8. So this relationship works both ways. When Carrie was 10, Kim was 12. When Carrie was 16, Kim was 18. When Kim was 25, Carrie is 23. When Kim was 40, Kim was 38. Carrie was 38. When Kim was 50, Carrie was 48. And when Kim turned 70, Kim was 72. And again, we could have just gone 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and that would have been just fine. But here, since the relationship is 2 difference, we could have picked anything. We could have said when Carrie was 453 years old, means Kim was 455 years old. So that relationship continues all the way through. Now, as far as an equation goes, we can write 2 different equations here, and it really just depends on what we're looking for. We can come up with Carrie's age if we know Kim's age. C equals Carrie, and K equals Kim. We can also come up with Kim's if we know Carrie's. To find Carrie's, I can take Kim's and subtract 2. Let's check it. So if Kim is 7, Carrie, I can take 7 minus 2 and get 5. To find Kim's age, if we know Carrie's, I can add 2. Carrie's age plus 2 gives me Kim, because Kim is 2 years older, so wherever Carrie is, we have that additional 2 years older that we add on to Kim. And Carrie's 2 years younger, so we take Kim's and we subtract 2 to get to Carrie. So either one of those work. If you're going to use X and Y or smiley face and sad face or whatever you want to use for your variables, make sure you tell me what they are. Here with C and K, we could probably figure it out, but make sure you define those variables so that everybody's on the same page. Now, as far as the graph goes here, we have Carrie's age and Kim's age, and I'm going to go by ones here. We could go by 5s or 10s or 3s or whatever we wanted. It doesn't matter, but I'm going to just go by ones. Remember, this point right here is 0, 0. So 0, 1, 2, 3, and so on. One thing to remember here, guys, is that the space between each of our squares here on our graph has to be the same. And it doesn't have to be the same on the X as it is on the Y, but the gaps between them have to be equivalent. So here I went 1 each time. I increased by 1, I increased by 1, all the way through. The same thing over here. Every time I go up by 1. I could have done like by 3 down here and by 10 up here if I wanted to, depending on our problem. That's okay. They just have to be consistent. So if I went by 3s, it would have had to have been 0, 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33, 36. Okay, it has to be even. Now, we know that when Carrie was born, so 0, that Kim was 2. When Carrie turned 1, Kim turned 3. When Carrie turned 2, Kim turned 4. And we can continue this. When Carrie turned 10, Kim turned 12. When Carrie turned 6, Kim is 2 years older, so she was 8. And we can draw a line through here because time is continuous. So even though they might have only said she was 5, she was actually like 5.75 or something like that years as time went on. And that continues for both of them. So since time is continuous, meaning it goes on and on and on and on, we can draw in our line there. We can also put an arrow on our top end, our upper limit, because they're going to keep going. Here, my last point is at 10, 12, but they could be 45 and 47. They could be 98 and 100. So it's going to keep going in that direction. I cannot put an arrow on this end, though, because we can't have negative time. So we got to be careful there. Inductive reasoning is the process of reaching a conclusion based on an observed pattern. We can use inductive reasoning to predict values. So in example 3, we're going to extend a pattern. This is on page 63, so there's a picture in your book. It looks very similar to the one that I have here with figure 1, figure 2, and figure 3. The table shows the relationship between the number of blue and the total number of tiles in each figure. We're going to come up with our table and then extend it and find the total number of tiles in a figure with 8 blue ones. So here I have 1 blue and 9 total. In figure 2, I have 2 blue and 3, 6, 9, 12, 15, 18 total. In figure 3, I have 3 blue and 27 total. And it looks like our figure number tells us how many of these big squares we have. And each square has 1 blue tile and 9 total tiles. So in figure 4, I'm going to have 4 blues in the middle and a total of 4 times 9, 36 tiles. In figure 5, I'm going to have 5 blues in the middle and 5 times 9, or 45 total. If we wanted to find for any term, let's say n, figure number n, could be 100, could be 371, could be 291, doesn't matter. Okay, I know that the number of blue tiles is going to match my figure number because that's how many of the big squares I'm going to have. And the total number of tiles is going to be how many big squares I have times 9. So how many blue tiles I have times 9. And we can see that here. I go from 1 to 9 by multiplying by 9. 2 times 9 gives me 18. 3 times 9, 27. 4 times 9, 36. 5 times 9, 45. So n times 9 gives me 9n. So if we're looking for 8th figure, that tells me I'm going to have 8 big squares with blues in the middle. When I multiply that by 9, I'm going to have a total of 72, or 8 times 9, total tiles. We can do this on a graph as well. Blue tiles go up by 1 every time, so I'm going to make my scale go up by 1. My total tiles, though, go up by 9, so I'm going to make my graph go up by 9. We wouldn't have to. We could go up by 1s, 5s, 10s, but this makes it easiest so that we don't have to actually try and figure in the middle. We don't have to guess and say, well, 60 is about right here. We're not trying to do that. We're trying to get as accurate as possible and also to show as much information as we can. So we could have just gone by 1s, but then we would have only had 1 point, and we want as much information as we can see here. We want to see the whole pattern. So when there's 1 blue tile, we have 9 total. When there's 2 blue, we have 18. At 3, we have 27. At 4, 36. At 5, we said 45. At 8, we said 72. And this pattern continues, so we can continue it up all the way through. We can also put an arrow on it going in the positive direction. We can't in the negative direction because we can't have negative amounts of tiles. We also cannot connect our dots here, because if we were to connect our dots, that would mean that we could have 4.3 tiles, for example. We could have 8.1 tiles, and that's not something that we have. We have complete tiles. We have whole tiles. So since we can't have partial or in-between amounts of tiles, we cannot connect our graph here. We keep it as just the dots. Last thing we're going to do is write an equation, and we've already kind of done that. We're comparing blue tiles to total. And we said that our total number of tiles is 9 times the number of blue tiles. So we did that with our table. And I would suggest that as a place to start. Or from our graph, we could have seen that every time we multiply by 9. But getting the information organized that way and we can see what happens to take us from one place to the other is helpful. So I used B here for blue. So total equals 9 times the number of blue. And we got that on our table here by checking our pattern. Every time we multiplied the number of blues times 9 to get our total. and I'll continue on in another video.